Assalamu alaikum, guys. Today I'm gonna finish the deflection of beams using virtual work method. Here I'm just gonna show you a couple of examples on the method. So, example number one. With this example, I would really like to use the same beam that we actually used for the derivation of the virtual work method. And my objectives in that is actually twofold. Number one, I just want to show you how the value or how PD will cancel out from the equations. And number two, I would also like to show you how we deal with formulating the moments functions when we have two different concentrated force and how we deal with that. Okay, so first of all, I'm gonna call this the real system, right? Because this is what we're after. Here we want the deflection at point D, and we know where the load of PC is. And as we said, when we want to do that, we just assume a virtual load, which at this point in time, that we don't know what the value is at the point where we would like to find what the deflection is. So this now becomes what we call my virtual system. Okay, so with that, what we will do, we will find first of all the reaction for each system. Okay, this is my real system again, real, and this is my virtual system. Okay, so as you've seen, I found the reactions for each, and now I would like to start finding the moment function. So what do we notice here? We notice here that we have what I would call three parts. Why? First of all, this is going from A to C, right? Now, if I wanted to find, let's say, the deflection under C, then when I'm using my virtual force, it will be put on point C. Then I only have two sections from A to C and then from B to C. But since this is going from, I have another force at D, then I would also need to have another section from C to D. So I'll be calling this, let's say, X1, and then this would be X2, and then I have the rest, which is X3. And since both the virtual system and the real system must have the same origins, same limits, even the same sense of positive moment or positive shear, okay? So again, this will also need to be defined as X1 right there, and then I have another X2 over here as well, and then this is going to be my X3. Okay, as you notice, the limits of X1 is from 0, I'm going to put that up here, is from 0 to L over 4, right? And then this, again, and this is also from, since this is L over 2, okay, then L over 2 minus L over 4, so this also will be from 0 to L over 4. And then the rest is from 0 to L over 2. And the same obviously goes for the virtual system as well. Okay, so this is how we're going to start off doing. As far as finding the reactions, we did that before, and it's just simple equilibrium equation, so you should not have any problems with finding the reactions. If you want, just as a reminder, if this is force P, and this distance is A, and this is B, and the whole length is L, then the reaction here is simply P times B over L, and then this reaction over here is simply P times A over L. Okay? So you could use that instead of using the equilibrium equations. And we talked about that, I think, during chapter 3 of the text, when we start drawing the moment diagram and shear for standard simple beams. Now, so when we do that, then we take now these sections, X1 and X2 and X3. First of all, you've noticed that X1 I started from A to C. Okay, X2 when I say C, okay, C is just before the concentrated force, okay, and then X2 starts just after the concentrated force, which means that the concentrated force is not actually in, and the reason for it because it's a point of discontinuity. As you know, when you will know that, you've noticed that when you draw the shear diagram. Okay, so I don't enter them into my function, so I just go before and then I just go after. Then the question is, so okay, and you're gonna tell me, so why is this 3/4 PC and this is PC over 4? Shouldn't, when we close the gap at C, shouldn't they cancel out? And obviously they don't. And the reason for that is no. Because what do I have? Well, if you look at C itself, here is my PC, right, which I failed to show here. So now we know if I take this section by itself and do an equilibrium equation, summation of Fy is equal to 0, then this 3/4 PC, which is going upward, must equal 3/4 PC for this going downward for equilibrium purposes, right? And then the moment is just simply 3PC over 4 times L over 4, hence the value 3PC L over 16. Okay? So when I go now to this over here, so since this is downward, then this must be upward. And this is again 3/4 PC. If I do summation of Fy equal to 0, then this must be equal to now PC over 4. The summation of both, okay, is going to equal to PC. So now I take this part, which is just after C, and as you've noticed now, this is opposite to that, okay? Now if I close this section with this, they're going to be equal, and I'm going to close this section with this, and now these are going to be equal, okay? And obviously the moments are also present. This is going to be the moment like that, and this is going to be the moment like this, okay? So that's why these two are in the same direction but with different values, okay? So then when I move to X2, now this is my PC over 4, and now this is the moment 3PC L over 16. Again, if you take the moment at L over 4, you're going to get PCL over 8. Okay. If you do not want to work from this side, you can work from this side. Then the moment at this point is going to be PC over 4 times this distance, which is L over 2, as we've shown you before, and this moment is going to be PC times L over 8. Okay, and then the summation of Fy is going to be like that. So now I have taken 3 sections. I know what my forces are. I know what my moments are at that point. Obviously, I'm going to need these for my equilibrium, for my moment function. Okay. If we go to the virtual system, it's basically the same. Let me just remove that. Don't get confused. Okay, right. So I'm doing the same thing over here as well in the virtual system. The only difference now, what I did under PC, I'm going to do it under PD with the same thing, and I leave that up to you. Okay, and what we're talking about is obviously this section right here. So again, use a summation of Fy equal to 0, summation of M at X equal to 0 to get all these values that you want for each section. Okay, again, I'm not going to do that for you because I already did PC for you. Just do that as an exercise. And you won't be sorry. So now with that, I'm going to prepare this table that I usually do for when I solve virtual work method, and in that heading I specify the section, the origin, the limits, the real M over EI function, and then the virtual function, moment function. I usually refer to the real moment as capital M, and for the virtual I always refer to it as small m. So this is just a nomenclature of mine. If you want to do something else, I really don't care. Okay, so one of the things that I do care about is when we do this, again, same origin, same limits, same sense of positive direction. So if you chose your moment clockwise to be positive, then it has to be positive for all. You want your counterclockwise to be positive, then it has to be counterclockwise for all. For shear, if you want the upward direction to be positive, upward I mean this way, then it has to be for all. If you want the clockwise moment to be positive, then again it has to be clockwise for all. So now if you go back to section X1, which was section AC, we chose the origin to be on A, and then the limit was from 0 to L over 4. Then for that I simply just have the reaction, which was 3, 4 PC. Again, X1 was this way. Then this is my moment and this is my shear value. Okay, here I'm interested just in the moment. Then summation of moment at X1 is equal to 0. Again, here I'm choosing the positive direction as the clockwise direction, so that will be 3/4 BC times X1 simply. Okay, so here it will be 3/4 BC X1 minus M equal to 0, then M is equal to 3/4 BC X1. The same can be said for the virtual system. Here I have PD over 2. Multiply that by X1 and you get also the moment for that as well. Okay, again, same sense of direction for both the moment and shear. If you do that, you will get wrong answers. Now if I go to section CD, I'm going to choose my origin at C. Again, the limit is from 0 to L over 4. Now here, because of the presence of the moment, which is my 3 PCL over 16, and here my force is pointing downward, right? This was my PC over 4. Again, this is my X2. Then my moment function would be, again, I'm choosing the positive direction in clockwise, so this will be now 3 PCL over 16 times X1 minus, because this is now counterclockwise, I know, no CX1, I apologize, just 3PL over 16 minus PC over 4 times X2, okay, which is what I have over here. And the same thing goes for the virtual system. Here my concentrated moment is PDL over, well, not concentrated, the internal moment is PDL over 8, and because the force is in the same direction, which is giving me a clockwise rotation, then that's why this is positive. Okay, now PD, section BD is the same as section AC. Here I chose the origin to be at B because it is simpler, and the limits are from 0 to L over 4. Then the same as section AC, but now with different reactive force. So this is now 1/4 PCX3, and then this is 1/2 PDX3. As you've seen, you chose X1, X2, X3. In future examples, I'm just going to use just simply X, knowing that it is at different origins and different limits. So carrying out this integration, which is rather lengthy, then PD times delta D is equal to 1 over EI. Here is my capital M, and here's my small m. Okay, so this is M, and this is M. dx1 from 0 to L over 4 plus 1 over EI. Now this is also from 0 to L over 4, or 1/4 L. Again, section AC, section CD. Here is my capital M, and this is my small m, or lowercase m, whichever. dx2 plus 1 over ei from 0 to L over 2, again, m, small m. And now this will give me, when you carry out this integration, it's going to be 7 over 768 ei L cubed PC P delta, which, as I said, this will cancel out with this. So now delta D is 155 L cubed PC divided by 12,288 EI. Now, since PD is going to cancel all the time, I'm just going to use the virtual force as 1 kilonewton. Okay? Because we know it's going to cancel out, and it's just simply, it's a lot simpler carrying the 1. Okay. With that, let's do another example. Here, I'm going to use the virtual work to determine the rotation at A. So, this is a little bit different. It's not a deflection, it's a rotation. So again, this being my real system. Since I want a rotation, what causes rotation? Well, we know what causes rotation is the moment. So then my virtual force or virtual moment is going to be this, applying a moment at A, since I want to find theta A. So now this is my virtual system. I haven't talked much about the sense, whether I should use this. Okay, now here I chose the direction to be clockwise, and here I could have chosen it to be counterclockwise. It really doesn't matter which direction you choose. It will work out at the end. So if my choice of clockwise is correct, then I will get a positive answer. If it is not, I will just get a negative answer. Okay, so don't worry about the right sense of the rotation, and at the same time also don't worry about the right sense of applying the force, whether it's going to deflect downward or upward. It really doesn't matter. If you get a positive answer at the end, then you know that the direction you chose at the beginning was correct. If not, it's just going to be a negative value. So don't fret or worry about that too much. Just assume any direction and move on. So again, like we did before, here I have to find the reaction. Again, using the same technique, this 80 kilonewtons is simply 120 times 4 divided by 10. Then this is just simply 40 times 2 divided by 10. 120 times 2 divided by 10. Okay. As far as this goes, since the moment is going to be clockwise, I need a counterclockwise couple to counteract this 1 kilonewton. Hence, I have 1 over 6 this way and then 1 over 6 in the other direction. Okay, remember the reactions perform a couple when I only have a concentrated moment applied to any beam. Okay, so the action always will act as a couple. So since this is clockwise, then my reaction should be counterclockwise. Okay. Here, I really don't need more than 2 sections. Okay. Because of the concentrated force, I'm going to use section AC. I'm going to use the origin at A. The limits are from 0 to 2. And my M over EI is just simply 80 times X. And for the virtual system, small m, it's going to be the moment. Again, now this is going clockwise, hence the positive 1. This is going counterclockwise, minus 1/6 x. Now if I go to section BC, I can use the origin at, no, that's not the origin. Let's see, this is the origin at B. Okay, then the limits are from 0 to 4, simply 40x and 1/6 over x, 1/6 x. Now, if you chosen the origin at C, then you have to go in at C, find the moment that is there, and then instead of having 1 term for the integration, you're going to have 2 terms for your integration. And the same goes for, actually, you're going to have 2 terms here, and you're going to have 2 terms here, and then the integration will kind of be a little rather lengthy. And you do not want that. Always choose the origin that will give you the least amount of terms and the easiest one to integrate. Is it wrong to choose C? No, it's not, but again, it is lengthy. I did not. So for me now, theta A is just simply 1 over EI. The integration from 0 to 2, 80x. 80, this is my M, capital M. This is my small m. From 0 to 4. Again, this is now 40x 1 over 6, and then it's going to be 800 over 3 EI, which is 266.67 over EI. So this is your theta A. Since the value is positive, then theta A is going to be clockwise, which we always knew, right? So this was my deflected shape, and this is the tangent, and this is my theta A, and it is clockwise. Okay, now, so the way of an integration, I have another technique, and this is totally left up to you. Some people like it, some people don't. And this is just simply, instead of using the integration, what we usually do, we draw the moment diagram for the real system, and we draw the moment diagram for the virtual system. This is the virtual again, and this is the real system. Now the moment here is just 120 times 2 times 4 over 10, which we usually call PAB over L. So this is 160 EI, and this moment here simply is 1 kilonewton meter. We don't need that. Then the moment is just this. Again, I draw on the tension side, so this is positive and this is positive. Okay. The value is 1 kilonewton meter. Here again, you don't need to find the reaction for that. So what this theory states, you calculate the area under the M over EI diagram, okay, which is what I did over here. So this is equal to 1/2 times 6 times 100 over 60 EI, and I just take in the EI out. And then what you do, you find the centroid for the M over EI diagram, okay, which is what I did here. So this centroid, which is at 3.33 meters from this, so I go now for the virtual method, for the virtual moment diagram, and I go 3.33 meters, since this is the location of my centroid, and then I go here and find this ordinate, which I'm going to call YC. Okay, so what I'm finding is the value of this moment right here. Now we always know that this is simply 1 over L, which is 6 times X. Okay, now X is being 3.33, which will give me this value right here, which I did kind of over here. And lo and behold, it's the same value, 266.67 EI. So what this is basically saying, you take the area under the real system and then multiply that by the value at the centroid of the virtual system. Okay, so you find the centroid for the real system. Okay, hence the 3.33, which is 1/3 A plus 2B if you're going this way. If you go from the other direction, it's just going to be 1/3 2A plus B. Okay, with this being A and this being B. If you don't have that memorized, then what you need to do, you take this part by itself, which is just 1/2 times 2 times 160 EI, and then you find the centroid, which is this distance right here. You take that over here and find that the corresponding value under the virtual moment, and then you take the other triangle, and that's going to be 1.5 times 4 times 160 EI. Again, you move the 2/3 from this, and then you take this value and find it from here. if you're not comfortable using the centroid for this triangle. This method works for if you have a triangle like this and a triangle like that. If you have the parabola, okay, actually let me erase that. This is going to be for this, I'm sorry. Okay, so if I have this parabola and I have also a triangle like this for the virtual system, or like that, you can use the same technique. You find the area under this, and then you find what where the location of the centroid is. Okay, so if this is the centroid, then you take this over here and find that value, or you go over here and find that value. Okay, so you can use the same technique for this. Also, if you have a trapezoid, then you can use also the same. Again, so this is being M, okay, and this being virtual. Again, if you want to, I'm just leaving that out there for you. I'm going to use that technique once more in the frame part. Okay, if you don't like it, don't use it. Just go for the integration. Okay, if you think the integration is a lot simpler, a lot faster for you, just do it. All right, don't do this. Okay, but again, I have to give you different ways of solving the problem. Now here I'm going to use a little bit more involved example. Okay, and this here I want you again use the virtual work. I want you to find delta C and theta A. Okay, so again, this is now my real system. Since I need delta C and theta A, I need two virtual systems. So my virtual system number one, I'm going to call it. I'm going to put the virtual force at C to find delta C. Again, I'm going to use 1 kilonewton. And then my other virtual system is going to put the value of theta moment at A, which is 1 kilonewton, to find theta A. Right, so here I have only two virtual systems to find two different things. Okay, this one will get me delta C, and this one will get me theta A. Okay, so I'm going to use the same approach. I'm going to find the reactions for this one, and again, at this point in time, you really should know how to find the reaction. Take the summation of moment at A is 0. A equals to 0. Okay, then from it you find by, then summation of fy equal to 0, and you get ay. Okay, we do the same thing for the virtual system. Again, we find the reaction, right? And for the moment, it's the same. Again, this moment is going to do a couple on the beam, so this couple is going to resist this moment. This is going clockwise, so this has to go counterclockwise. All right, so again, this is going to be 1/4, hence the quarter and the quarter over here. Here, just simply take the summation of moment at A equal to 0, like we did with the real beam. You get by, summation of fy equal to 0, you will get ay. Okay. Now, again, here you would say, well, here I will take section DA, AB, BC, and I would say you would be right. But what we notice in the virtual system is that the moment DA is equal to 0, right? M here is 0, and M here is also 0. Okay, so there's no forces, there's nothing here, right? So these two parts have 0 moments. So even if I find the moment function for part dA in the real system, I will have to multiply it by 0 for delta C, and I would also have to multiply it by 0 for theta A. So there's really no need to find that. Okay, so I'll be just concerned by section AB and section BC. And that's why I've chosen these two sections. So again, I'm choosing section AB. I'm choosing the origin at A. The limit is from 0 to 4. Now from section CB, again, I'm going to choose the origin at C because it's a lot simpler, and I'm going to take the limits from 0 to 1. I'm going to postpone talking about M over EI. I'm just going to go to M1 directly. Here you've noticed that since I only have the reaction and there is no moment, and this is going, again, counterclockwise is negative, hence the value minus 0.25 times x, okay? If we go to M2, which is for theta A, again, this corresponds to delta C, and this corresponds to theta A. Then some people don't call these M1 and M2, they just might call this to be MC and M theta. Again, like I said, I don't care, right? So I'm going back with my terminology, this being M1, so this is minus 0.25x, and now this is because of the moment here is 1 minus 0.25x. If we go to section BC, here I have, again, the 1 kilonewton, and that will give me a moment of minus 1 times x. No force, moment is equal to 0. Okay, now I go back to the real system, and I actually did it for you. Here I have to do the same thing. Here I have, when I say from A to B, just after A. Okay, so my function is here. That's what I need. But to get to that point, I need to find out what this moment is, and I need to find out what this shear value. Okay, so for that I have to go back all the way to section DA. Now just before A, I know that my moment is going to be 30 times 2 times 1, hence 60 kilonewton meters. And if I do summation of Fy equal to 0, then this is going to be 30 times 2, hence this is the 60. Right, so I have these moment. Now I go to the support A. Now this has to be equal and opposite, hence I'm talking about that. Actually, let me change color. So I'm talking about this moment has to be equal to that moment, and this force has to be equal to this force in opposite in direction, hence the value 60 kilonewton. Now I do a summation of Fy equal to 0. Okay, so now it will be 131.25 minus 60, and I will get 71.25. Again, this moment is equal and opposite to this moment. Now I get to just after A. Now this moment again is 60, and now this force is 71.25 kilonewton. So when I write the moment function for that, this is what I'm getting. Again, this is the moment is counterclockwise, hence minus 60. This is producing a clockwise rotation moment, hence plus 71.25, and this is simply, again, and this also is giving me a counterclockwise, so this would be 30 times x over 2, okay, so 215, and hence the value of minus 15 x squared, okay. So this is how I got the moment function for the real system. Okay, as far as this one goes, again the origin is at C, so this is going to be my 30 kilonewton meters. This is the force, so this is going to be my moment, and again this is just simply 30 times x over 2, which will lead to minus 15x squared. Okay, so simply doing the integration now, and that's what I meant when you have multiple terms. It's going to be 1 over EI from 0 to 4, again this being the M part, this now being M1, again this is being M, and this is being M1, so now this is equal to minus 20 over EI plus 37, and it's telling me that it is minus 16.25 over EI, and it's telling me that I have a negative deflection, which means that it's going upward. I thought it would bend downward, but it didn't. Okay, again, like I said, doesn't matter what you chose. So from that, I'm getting a negative value. So now probably the deflected shape is going to be something like that, okay, because I got a negative value. So if I, let's say, chosen my virtual system from the beginning to be like that, then this would be positive. Again, it really doesn't matter, right? Theta A, no, this is going to be M, and this is going to be my M2. Again, here I'm getting a negative value, and because it is negative, then I assumed the original direction to be clockwise, so now it's going to be counterclockwise. Okay, so that's that. And this will conclude my presentation for the examples on the virtual work method. The next one I'm going to be dealing with frames. You guys enjoy your day and stay safe.